This video we're going to look at some graphing, and we're going to use the graph for time and distance that's on page about 13 in your physics booklet. And it's given us time and distances that we're going to plot. I've got a different piece of graph paper here that we're going to work on, but I want to try to get across how you would approach starting putting a graph and use some terms. We're going to calculate a slope and try to use some of our better physics practices. So first of all, my data is over here. I've got time, and my time runs up to 40 seconds. So for any distance time graph, the distance in meters goes on the y-axis and time in seconds goes on the y-axis. And every time we graph, we try to put the thing that is the manipulated variable on the x-axis and the responding variable on the y-axis. But if it's something like distance versus time, distance is going to be on your y-axis, time is on your x-axis. If it was something like velocity time, velocity goes on your y-axis and time goes on your x-axis. We don't have control over time, but it's easy to measure. And so it's perhaps not manipulated, so to speak, but we are able to set what the intervals are that we're going to record things. So here we're going to be plotting up to 40 seconds. So one of the things I need to do is pick my scale. And anytime you're scaling a graph, you need to know what your higher points are, as well as what your total number of spots are, or graph marks. So if this is going to be 0, this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that's a little convenient. I'll make it a little bit longer. But essentially, I'm going to be setting each of these little gradients. So if I've got 20 gradients and I've got 40 marks, I'm going to be making each of these about a 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. We actually don't probably really want to fill up all of the lines on the graph. It doesn't allow us to kind of extend our graph past our measurement, but we want to fill up at least 2/3 of the graph paper. So on the next one, you can see we've got a value of 21. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I don't actually have enough to be able to make each line worth 1. So I'm going to go, I think I'm going to go by 2s again. I'm going to go by 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now it doesn't quite fill 2/3 of my graph, so that's not actually very ideal. I'm going to erase that because I feel like that doesn't support good graphing. I'm going to go up by every 2 of these will be 3. 3, 6, 9, 12, 15, 18, 21. So it's not perfect because I'm not going to be able to exactly line up with the graph line for each of these numbers, right? They're not going up nicely by those exact numbers, but that's not really what the expectation with a graph is. So the idea is the more of the graph paper that we fill, the more precise it is. We're not looking for the exact lines to always be perfect. We're wanting to get our graph to fit into the graph and fill the graph kind of as much as possible. So my first point is going to be at 0, 0. So now I'm going to draw my point here, and I'm going to draw a little circle around it so it's easy to find. I'm using red here so that it kind of pops. My next one is going to be at time of 5 seconds. So that's halfway between 4 and 6. And it's going to be at 2. So I'm going to put it about here because it's not, it's a little ways between a little past the halfway mark. So if I really was probably being a little bit more careful, I'd make it a little bit closer to the line here. And I need to make sure that it lines up. So I'm going to go there. And then my next is at 10 seconds. And at 10 seconds, it goes to 4. So this one's going to be about here-ish, maybe a little bit more like that. And then we have 15 seconds, which is halfway through here. And so 15 seconds, there's 8 meters of a distance. So halfway between here would be, that'd be 7.5. So it'll be a little bit higher than that one. So I'm going to put it about here. And then at my, sorry, and that was time 15 seconds. So 17 seconds is going to be about halfway. Oh, hold on. Sorry, 15 seconds, and it was at an 8. So 20 seconds is my next mark, and at 20 seconds, I get 12. And this is a nice one because it lines up with 2 spots on the graph exactly, so it's going to be nice and easy to plot. And then I'm going to get at 25 seconds, it's going to be 15. So this is another nice one because at 15, it's going to be about there. And so you can see I'm plotting my points, and it's going to kind of drive you a little bit crazy. I'm sorry you're having to listen to me. 30 seconds, I'm going to 17, and 17 is about here or so. And then we get 35 seconds, we get 19. 19 is going to be a little bit further along, about here. And then at 40 seconds, we get our 21, and 21 happens to be another nice line here. So here we go. Okay, so my line of best fit is going to go between and try to get as close to the points as possible. This might not be perfect, but I need to try to line it up as well as I can. And I'm not going to hit every point. It is not connect the dots. So this is my line of best fit. Now, after this, if I wanted to continue the line, it's called extrapolating. So this section that is in here is extrapolated. And in between the spots, we are interpolating. So this is an interpolation and an extrapolation of our line. When we are calculating slope, one of the challenges with slope calculations are that I want to pick a spot that I have not got as a point. So even though this point happens, some of these points happen nicely on an intersection, I want to select my points for calculating slope. So slope here is going to be equal to rise over run. So it's going to be equal to x2 minus, or pardon me, y2 minus y1 over x2 minus x1. And that'll give me my slope. So I need to pick my 2 points, and I'm going to pick this one. This looks like a beautiful point to me because that point is going to be 6 seconds and 3 meters, right? So I'm counting off of here. It's 6 seconds and it's 3 meters. And it's nice because it lines up in an intersection. It makes it pretty easy to find it. This point also looks pretty good. It's a little harder to see. So that point is at 24 seconds, and it is at halfway between 15 and 12. So that's going to be 13.5 meters. Now, to calculate the rise over run, my x2, or my y2, sorry. My y2 is this number. So it's going to be equal to 13.5 meters minus 3 meters. So that's my y2 minus my y1 divided by my run, which is 24 seconds, minus 6 seconds. And so I'm going to get the difference between these. It's going to be 10.5 divided by 18, so 10.5 meters divided by 18 seconds. And I don't happen to have my calculator right on hand, so I don't have the number for that. But it should have, looks like 2 significant digits, because all my times are reported as 2 significant digits. And that's how we're going to approach our graphing. So we want our graph to fill, our numbers to fill most of the graph. We want the scale to be consistent so that we're always counting up by the same increments, right? So this was 2, 4, 6, 8, 10, and then 3, 6, 9, 12. We want to plot our points, and when we calculate, or when we draw our line of best fit, we should reasonably be using a ruler. We're going to interpolate it, and then if we have to extrapolate to go past the end, we can. And we are going to finally calculate our slope with points that are on our line of best fit, but were not actual measurements that we were given at the beginning here. We don't want to use those numbers. We want to use numbers from our line of best fit. So that's how we accomplish our graphing.